Hello, everybody. Chapter 31. I think if I go through this chapter in this video, we will have enough time next week to cover the things that we need to wrap up this course. My apologies for missing another class. I feel bad about that. I'm sorry. Last couple days wasn't doing terribly well, but much better today. So I'm able to make this video for you. So, Chapter 31. We are going to be talking about Faraday's law primarily, but before we can do that, we have to introduce this concept of magnetic flux. Magnetic flux. You may remember electric flux, where we talked about how much electric field passes through a given area. Magnetic flux is about how much magnetic field passes through a given area. And often in this particular case, we're going to have a very well-defined area in the sense that we're going to have a physical bit of wire that's forming an area, and the current, the magnetic field could be passing through that. So as you can see here, hello by the way, is we have a loop of wire that, well, you can see it's kind of perpendicular to the screen. It's set up in such a way that the magnetic field is flowing directly through here. So there's a lot of magnetic field that's passing through. But if I were to tilt this some, you can see tilting it backwards. Well, there's if you look at it from this side over here, there's less room for the magnetic field to get through. So there's less electric flux. If I keep tilting it, as you can see over in this pane, well, now none of it can get through. It's all just sort of flowing by. So you can see how this angle affects how much magnetic field can get through. And we can define an equation for the magnetic flux. We're going to use the same symbol as before, except we're going to use a subscript B this time. Is equal to B magnetic field dot A, which is the area vector. The area vector. So the area vector is a vector that points perpendicular to the area and has a magnitude equal to the area. Points perpendicular to the area and has a magnitude equal to the area. So if I were to expand out this dot product, this is going to be the magnitude of B times the magnitude of A times the cosine of the angle between them. And then look down at this first pane, the area vector points that direction, such that it's pointing in the same direction as the magnetic field, which means that, yeah, the angle is 0, which means that I just get a magnetic flux in this particular case of BA. So I have the cosine of 0, that goes to 1, it's just equal to B times A. In this particular case, you can see that the area vector points that direction, so that there's this angle in between the magnetic field vector and the area vector. You'd use that angle in your calculation. And then over on this pane, the area vector points straight up. So theta here is 90, which results in a magnetic flux of 0. This equation works if we have a regular area and uniform magnetic field. If you were to have to do problems, which we're not going to do in this class, don't worry about it, for a more general case, we could say that in general, the form of the equation is the same, but it is the integral. Magnetic flux is the integral of B dot dA, where you would integrate over every little piece of area and how much magnetic field is passing through that. The equation you really need to remember, though, is this one at the top, which is about how much magnetic field passes through an area. Now, unlike what we did with the electric field, this is going to end up with a very, very practical result, which is known as electromagnetic induction. Electromagnetic induction, the overall concept of electromagnetic induction, which sounds incredibly fancy, I will agree, is that the idea of changing magnetic flux, we just learned about magnetic flux, can produce an electric current in a circuit. Changing magnetic flux can produce a current. And if you think this through, everything we've talked about with magnetic fields, this should start to make a little bit of sense. Notice it says here that currents, moving charges, produce magnetic fields. And then the opposite is true, that if a charge is moving through a magnetic field, it feels a force. So it starts to make sense that maybe if instead of just a stationary, like regular magnetic field causing a force on a moving charge, what if I sort of reverse this and had a magnetic field that's changing in some sort of way? Maybe you can extrapolate that to imagine that taking a charge that's not moving and causing it to move. And that's sort of like a really rough idea of what's happening here, okay? So what's going to happen is that we're going to get like sort of like a magic current that gets produced in a circuit that's not connected to a power source or a battery or a source of potential at all. Notice down here in this diagram, I have a coil of wire that's just connected to a meter that just tells us how much current is in that wire. It's not connected to anything. It's literally just a coil of wire, but this is going to produce an electric current in this wire as if by magic, okay? This magical current is known as an induced current. So when it comes through this process of electromagnetic induction, that specific kind of current is called an induced current. Now, I can't have current flowing unless I have a place for the current to go, so a closed conducting path, and I have to give it a reason to flow, which means there must be a potential difference in here somewhere, and we call that potential difference that's sort of come from this changing magnetic field an induced voltage. So let me show you a little bit about how this works, and then we'll get into the details. First of all, this magical coil of wire that's just sitting here connected to nothing. Notice they are showing it as having current passing through it. It's passing through it because I have a bar magnet, and this bar magnet is moving closer to the coil. So you can imagine before the magnet even got there, it was like this coil of wire is just sitting there, and it's like, I don't feel any magnetic field. In other words, there's no magnetic field passing through the coil. But as the bar magnet comes closer, more and more magnetic field passes through, more and more magnetic flux is passing through this coil. That's a changing magnetic flux, which causes a current. If all of a sudden I stop, notice velocity equals 0. Even if this has gotten close and there's magnetic field lines passing through, there is magnetic flux, but it's not changing, there's no current. If I then decide to back this up so that there was magnetic field in here, but it's changing and less is passing through, notice now I get a current in the opposite direction. So it's all about changing magnetic flux. And we can use this idea of Faraday's law of induction. It tells us exactly how much induced voltage we get, and from that, if we know how much resistance is in the circuit, we can use Ohm's law to find how much current we get. So Faraday's law of induction looks something like this. This is the induced voltage, which again, it's being produced because of the changing magnetic flux, is equal to negative N, and let me see how I want to write this. Let's write it like this, first of all, times the change in magnetic flux over the change in time. Or we could write this if we can't define the change in such a linear fashion. We could say this is equal to negative N and use the derivative. Same idea. But you could use the one on the right if you're given a function for how the flux is changing instead of maybe knowing some discrete values for how much it's changing. We're going to do an example with this. This one you're not going to have to worry about so much. Okay? So what else do we have here? We know that we have a magnetic flux. We understand this is changing stuff. This N is the only other thing I need to tell you about. And this is the number of loops forming the area. The number of loops forming the area. This negative sign gets a whole slide of its own. That negative sign is essentially what's known as Lenz's law. Lenz's law tells us something about the direction of the induced current. So here's the way it works. We can say that the induced And let's do it in this direction. The induced magnetic field, current, and voltage are in a direction that opposes the change in magnetic flux. And this is where things get a little bit weird. It's almost like nature just wants to keep things the way they are. Whatever that happens to be, it's like, I don't like change and I'm going to fight it. It's a losing battle, but I'm going to do whatever I can to fight it. So for instance, if you imagine that I just have this bar magnet and just a single loop of wire, okay, and I bring the bar magnet closer and closer, that means more and more magnetic field is getting into this loop. There's more magnetic flux. It's increasing. And not only is it increasing, but there's a magnetic field that's increasing and it points in this direction. So what the loop does is say, well, I don't really care for this increasing flux that points to the right. So I'm going to create my own magnetic field. And again, this is just a loop of wire. I'm going to create my own magnetic field that points in the opposite direction to try to oppose this thing that's growing and pointing this way. Okay? So you can see they've drawn kind of a ghost bar magnet here because this is the direction of the induced magnetic field. Once I know the direction of the induced magnetic field, I can use the right-hand rule to find the direction of the induced current. So point your thumb in the direction of the magnetic field that's induced, and then your fingers will curl in the direction of the current that flows around the loop. So just by bringing the magnet closer, as long as it's coming closer, what happens is current flows around the loop in that direction. If I begin to remove the magnet, now you can imagine, okay, there's magnetic field that's pointing through the loop this way, and it's shrinking, it's going away, it's decreasing, and the loop doesn't like the change. So what it says is like, okay, if you're going to take my magnetic flux away, I'll just create my own. So it creates a magnetic field that points in the direction of what's being taken away from it. So this is B induced. And again, you can point your thumb that direction and your fingers tell you the direction of the induced current. So this is I induced, this is I induced. Okay? It opposes the change in the magnetic flux. And there's other ways that this could change. So for instance, what if I just had a changing magnetic field magnitude? So maybe there's this magnetic field that's being created by something. I don't know what. Maybe it's connected to like a master dial where someone can turn the magnetic field up and down. And then all of a sudden someone decides to turn it down. It decreases in magnitude. Notice the field lines, there aren't as many of them now. It decreases in magnitude. So there's less passing through this loop than there was before. Well, it's going to try to replace what was lost. So you can see they've added a few more field lines in here to try to get it back to the way it was before. It's the loop of wire that's connected to nothing that's producing a magnetic field in the direction of what was being taken away from it. So if the magnetic field decreases in magnitude, the induced current produces a field that opposes that decrease. It tries to replace what's being lost. So you can see that we get from the right-hand rule, B induced points this way, so the current goes around in that direction. Okay? So let's see, let's draw this in. This is B induced, and then going around that way is I induced. Okay? And then finally, you could just do something like change the area. So for instance, maybe we just have some sort of magical sort of thing. I don't know how to do this. Let's say we have a loop that's like this. And then we just take the loop and, I don't know, just smush this way. Just squeeze it in from the side so that there's less area for the magnetic field to pass through. Well, if I change the area, then there's going to be less flux, And anytime that happens, it's going to oppose the change to try to get the flux to whatever it was before, okay? So the best thing to do is to do a few of these multiple choice questions. This one is drawn poorly, so it's just not great to look at and causes problems. Here we have a loop of wire in green that's in a magnetic field that points into the screen. So magnetic field is into the page. And then something is just taking this loop of wire and pulling it to the right. Well, notice this is moving to the right, but the amount of magnetic field that's passing through the loop isn't changing. If it's not changing, there is no induced current. No change, then there's nothing to fight. On the other hand, if now this thing begins to leave the magnetic field, it's like, my magnetic flux is going away, it's dying, I'm losing it. This loop is going to create its own magnetic field to try to replace what's being lost, so it's going to create a B induced. Let's put that here somewhere. So we'll say like this, it's like, oh, I need to put my own back in here. So this is B induced to try to keep the magnetic field that's there, which means that the induced current will go around clockwise, I induced. And that's not going to last for very long, because as soon as it gets out of the field, now all of a sudden it's going to be a constant nothing, which it's going to drop to no induced current. So just while the change is happening, do you get an induced field and induced current? What if here it says that we have this magnetic field that's pointing into the page, but the magnetic field suddenly increases? So yes, it's being dragged this way, so like how much is getting through there isn't changing, but someone's turning up the power of the magnetic field, which means there's more magnetic flux in that direction. Well, if that's the truth, then it wants to oppose that increase by creating an induced magnetic field in the opposite direction, which will cause an induced current counterclockwise. So you might imagine that we get B induced out of the page, which results in a I induced around that direction. Okay, I don't know why this F is up here. That's weird. All right. Here, what if we have a coil of wire, and you can see the magnetic field is pointing into the screen, and now all of a sudden the coil of wire just shrinks. Well, that means there's a decrease in the amount of flux that can pass through it. So what it will do is try to add more of its own to try to keep the amount of magnetic flux the exact same. So that is going to be B induced. And again, right-hand rule points in the direction of B induced. Current is going to go with the fingers. So that means we're going to get clockwise current. Okay? And again, listen back through this again. Think about it. I know this is a bit of a confusing concept the first time. This is a poorly drawn picture that turns out being confusing. Let's take a look at this one. So in this particular case, sort of stop the problem before like it goes and falls all the way through. We're going to take a bar magnet and sort of drop it toward these two loops of wire. And then we're going to take a bar magnet and drop it toward one loop of wire and see what the difference is. So we're looking for the magnitude of the induced voltages in these cases. Well, here's the key. If we look at Faraday's law, it equals minus N delta flux, delta T. Well, in this particular case, keep in mind, well, the flux is going to change in the same way just because I have the same magnet that's following the same distance, etc. It's N that's changing. So this one has, we could say, 2 times the potential difference it's created, and this one is just the regular induced voltage. The difference here is that, let's see, what is this asking? It's the next one that's different. So compare the magnitude of the induced voltage. Number 2 gets more. So let's see, that is this answer. More loops, more induced voltage. But here it asks about the induced current. So while this one has twice the amount of induced voltage, remember it also has twice the amount of wire. So it has twice the amount of resistance. So over here we could write this using Ohm's law, V equals IR. This one is going to be 2 times the induced voltage equals I times 2R. And the 2's cancel, and we can say that we just get I equals that over R. And over here, well, I is equal to that over R. Nothing weird happened. The current is going to happen, so it's going to be non-zero, but they are going to be the same in both cases because you have twice the amount of resistance. Okay? Let's see. What if we have this loop of wire that's being pulled away from a current that's going straight up? Well, first of all, we need to imagine what kind of magnetic field is being created by this. We can put our thumb in the direction of the current, and you can see that over on the right side of the blue wire, we have magnetic field that's into the screen. So we have magnetic field that is into the screen over here. But then as we go this direction, the magnetic field is weaker because I'm getting farther away from the wire. So that means that as I go this direction, B is weaker. So we could say that the magnetic flux is decreasing. And we have magnetic flux into the screen that's decreasing. So it's going to try to reinforce that by applying additional magnetic flux in the same direction in an effort to reinforce what's being lost. Thumb in the direction of the magnetic field gives me a current that flows around clockwise. So that's I induced. Okay. What happens, though, if I have the same situation, but I move the loop of wire this way? Well, now it's staying a constant distance away from the wire, so the flux isn't changing. If the flux isn't changing, then there is no current. All right? Which brings us to a quick example, and let me scroll ahead to see what else we have here. Okay, we've got a few more things that we're going to do and some things that I'm going to leave out. Let's see. So let's do this example. We have a 100 turn, or that just means that N is equal to 100. Rectangular loop of length and height as given, and it sits in a region of uniform magnetic field of magnitude B is 23 millitesla. The wire has a certain resistance, and then it says that the magnetic field is going to start decreasing at this rate in millitesla per second. Millitesla per second. So let's see if we can find a few different things here. First of all, number one, let's see if we can find the initial magnetic flux. The initial magnetic flux. So remember, it is equal to B dot A, and that applies for every single loop of wire that's there. So I should write that as N times B dot A, because every one has flux that's passing through it. So that's going to be N B A cosine theta. But in this particular case, theta is 0 because the magnetic field and the area vector, which would be out of the screen, are in the same direction. So that's just going to be 1. So I have 100 times 0.023 times the area, which will be 0.15 times 0.062. So we can find this initial magnetic flux, and I've got that number here somewhere. It's 0.021 Tesla times meter squared. And again, it's magnetic field times area, so Tesla meter squared. So that's the initial magnetic flux. We can, let's see, also find the induced voltage. We can find the induced voltage using Faraday's law. So if I just want to find the magnitude of the induced voltage, then it's going to be N times the rate of change of magnetic flux, like so, which we could rewrite as N times delta, and we already know this is going to be NBA, because cosine of theta is going to give me 1 over delta t. The number of loops and the area are not changing, so I can take those out of the delta. So I have N, whoops, wait a minute, I got too many N's. I did N twice there, my apologies. We already included the N on the outside. This is just B times A. So let's see, the area is not changing. So I have N times A delta B delta T. And this delta B delta T is the rate of change of the magnetic field, which they gave us there. So this is going to be equal to 100 times 0.15 times 0.062 times the rate of change of the magnetic field. So in millitesla, need to be a little bit careful with that. That's going to be 0.00027 millitesla per second. So that's going to give me an induced voltage of, let's see, 2.5 times 10 to the minus 4 volts, from which we can find the current. So we could just say that the induced voltage is equal to I over R. So I induced is the induced voltage over R, so that's 2.5 times 10 to the minus 4. And they said the resistance was 12 ohms, so that gives me 2.1 times 10 to the minus 5th amps. So what direction is this current? What direction is this current? So again, it's decreasing. I have a magnetic field that's pointing toward us, and it's decreasing, which means it's going away, so I need more of it. So that means magnetic field induced, is going to point in the same direction, be induced, which from the right-hand rule tells me that I induced is going to flow around counterclockwise. So it's in the counterclockwise direction, okay? So there is an example. Let's see. Induced EMF in a moving conductor. So I'm not going to say too much about this. I just want you to see how it's true. First of all, we could write an equation for this in case you need it. It's equal to B times V times L. And it turns out this is just the velocity of the conductor, and this is the length of the conductor. Okay, and notice we're illustrating this two different ways over in the diagram to the right. So in this case, we have a conductor, that's the conductor that's moving to the right, and we've got it connected by a loop of wire. So you can see the length of the conductor here, and its velocity is to the right. It's sitting in a magnetic field that's pointing at you. So if it turns out the conductor is moving to the right, that means more of this magnetic field is getting through that particular loop. If more of that magnetic field is getting through the loop, it's going to oppose that and give me an induced magnetic field in the opposite direction. An induced magnetic field in the opposite direction gives me current that flows around this loop in the clockwise direction. So I induced is this way. The thing is, it works out that I don't really need the loop of wire. I could just have a conductor itself, just a bar that's moving through a magnetic field, and you're going to get the exact same thing happen because of the force on the free electrons that are inside that particular conductor. So let's see. You can imagine that I have charges, positive charges are in here, and they're moving to the right. And remember, we can find the force on a point charge. So it's Q times V cross B. So V is that direction, and B is towards you, which means on a positive charge, the force would be down. So the force is up on an electron. Notice, if that means that electrons separate and move here, there's going to be a dearth of electrons on the other side. That means I get a potential difference from one side of this conductor to the other. That's an induced potential difference. If you're wondering why any of this matters, what if that's an airplane wing? Ooh, an airplane wing is a conductor that's flying through the Earth's magnetic field, which would cause a potential difference to arise from one side of the airplane wing to another. It turns out there may be an example on this in your book. I actually have one that's here. Using some typical numbers for an airplane wing, it's something on the order of 1 volt. But it does happen, and it's something that has to be considered when we have conductors that are moving through an electric field. Okay? So let's see. We basically just did that example, so we don't need to talk about that. So what are some applications? Basically, we're going to wrap up this chapter by just giving you some applications of changing magnetic flux. So first of all, the electric generator. The electric generator is something that actually generates electric current. And if you've been thinking about what we've been doing, we've been creating a current that seemingly comes from nowhere. It just comes from the fact that magnetic flux is changing through a loop of wire. So if I were to take a permanent couple of magnets so that I can create a magnetic field between a north and a south pole, these two magnets, and then just put a loop of wire that's got that magnetic field passing through, and then turn that loop of wire, well, as long as this is turning, the amount of magnetic flux is always changing. And if it's always changing, it's always generating current. The thing is, in this particular case, because this is going to flip and then be the other direction, that means these two wires are changing, so these two are changing. What you're going to get is current that's induced one way and then current that's induced another way, and it's going to have a magnitude that's changing as well. This is how we generate an alternating voltage or alternating current, which we'll talk a little bit more about in the next chapter. So we put in the input ourselves. We do some mechanical work to turn the loop of wire through a magnetic field, and that mechanical work is essentially converted into electrical energy. The thing is that this works exactly backwards as well. What if I take current that's alternating, right? If I take the current and I'm always changing the current that's in here and I put it in a magnetic field, remember we said that if I have current that's going through a wire in a magnetic field, well, then that wire feels a force. And you can see that if it's a loop of wire, we briefly mentioned last time that would cause a torque. Well, this is just the reverse effect, and I'm going to get mechanical work. I can put in electrical energy that's alternating, and I'm going to get out mechanical energy by making something turn. This is essentially the motor for an electric car, if you want to think about it that way. It's an electric motor in general, but this is essentially how an electric car works. Take energy from the batteries and use it to turn the wheels, right? Transformers are another application, and we're not going to do anything with the calculations of this. Let me just point out that this is an electrical device which converts between different voltages. And it turns out, if you take a look at this diagram, notice I'm going to put in some electrical energy. But specifically, I'm going to put this in the form of alternating current, which means that the magnetic field that's being created by this coil of wire is like always in flux. Flux is always changing. If I put that near another coil of wire that has a different number of loops, well, then the amount of magnetic field that's passing through this coil of wire coming from this one is always changing. If the flux is changing, it produces a current. Ignore, if you want to, this iron core. This is all insulating. This coil is not physically connected to this so that there's no way for current to flow. It's just the fact that they're in proximity and the magnetic field of this one is passing through this one and changing. But the fact that I have a different number of loops means that in my the N in the equation, whatever voltage I have here, we're going to have a lower voltage over here because there's a different number of loops. And this works the other way as well. I could put my alternating current into this one and make whatever voltage I have here be higher over here because there's more loops. If you're wondering where something like this is used, just look at your cell phone charger. It has that little brick that's connected to it. It has a transformer in it. It's because the voltage that's coming out of the wall is too much for your cell phone or for your smartphone, so it has to be stepped down in voltage. There's a transformer in that little box that makes it, we'll say, a palatable voltage for your mobile device and gives you a voltage that's appropriate for that particular device. So that's transformers. This is also how electric power is transmitted. Generally, it transmits better with fewer losses if you transmit it from where it's created, well, or not created, where it's generated, to another place by using it at a high voltage. So typically you have those big transformers out on the power lines and like at the power substation and power plant that goes up to a really high voltage. And then when it gets closer to houses, it goes through other transformers that steps it back down in voltage before it gets into your house. All right. Let's see. So we're not going to do this. Boy, you got to love that diagram. Look at those lines. Those are beautiful. Yeah, that's nice. All right. And we're not going to do this. And we're not going to do this. You don't have to worry about it. Let me point out that just in general, this whole concept works. It's not just that changing magnetic flux creates a voltage and a current, but anytime I have a voltage and a current, there's also an electric field there. So we could say that in general, it also creates an electric field. So let me just tell you what the general equation looks like so you'll recognize it later on. So we'll say general form of Faraday's law looks like this. E dot dl is equal to minus ddt, like so. So this side has to do with the loop that's enclosing the area where the magnetic flux is changing. This is my changing magnetic flux, and we end up with an electric field that gets produced. That's the general form of Faraday's law. I'm not going to expect you to do any calculations with that. Which brings us to the last slide, which has some other examples that are around us all the time that use Faraday's law of induction. First of all, there's this man that's doing some serious singing. He's singing into a microphone. The way the microphone actually takes sound and converts it into an electrical signal is through means of a coil of wire. So what happens is there is a cone that can sort of catch the sound waves, and this is really, really lightweight, so that the sound waves hit this and will vibrate this cone, which is attached to a coil of wire, and that whole thing is sliding back and forth on top of a permanent magnet. So when that happens, you can imagine exactly how much of this magnetic flux is passing through the coil of wire, is rapidly changing in a way that matches the vibrations of the sound. And it turns out the tiny little bit of current that's produced in this coil of wire, that's not just a solid current, but it's a dynamic current. It's a dynamic current that matches in some way the sound can be sent to an amplifier and amplified and recorded, or boosted and played out over speakers, etc., etc., etc. Similar sort of thing for an electric guitar. There is a little magnetized portion of the string that is sitting, well, near a coil of wire, and as this vibrates back and forth, it's not unlike what's happening here. The magnetic flux is changing through this coil of wire, which means you're going to get an electrical signal that's changing. This says magnetic tape recording, but if you want to just think of this as the magnetic strip like on a credit card, well, when you slide the credit card through, this is a magnet, and it's a certain, very specific magnetic field that's going to be applied and changing through a nearby coil of wire in the reader, which generates an electrical signal that's changing, and it can be amplified and decoded and read. All of these simply involve magnetic fields that are changing in the vicinity of a coil of wire, which means that the magnetic flux is changing through that coil of wire, and that generates an electrical current that's also dynamic and changing and can contain information. So that is the end of chapter 31. On Tuesday, I will see you again, and we will work hard at concluding the material that's in this chapter. We may need Thursday as well, but we'll see how things go on Tuesday. Thank you for watching, and have a good weekend.